Here's a question from the IB High Level Maths 2019 paper, and it's a question about linear system. So we have three equations and three unknowns, and the question is, what are the parameters A and B such that the three planes, right, because those equations, they correspond to, each of them corresponds to an equation for a plane. Those three planes should not have any points of intersection, and we have to find the A and the B for which this is satisfied, right? And if you'd like to see anything similar to this on the channel, or if you have any suggestions for any problems that you'd like to see, let me know in the comments. So this looks quite tedious at first glance because we have three equations and we have three unknowns and we have two further unknowns in terms of A and B. So if we use the classical substitution method, this is going to turn into a mess, right? So it turns out that this is relatively straightforward to solve if we use matrices. So I'm going to start by writing the augmented matrix for the system, which is this. So we have 2, minus 1, 1, and then we have 1, 3, minus 1, and then 3, minus 5, and then A, and then we draw a line, and then we write what's on the right hand side. So that's 5, 4, and B, like this. Now, the first thing I would do before doing any row operations, any multiplying rows with constants and subtracting from other rows, I would first switch rows 1 and 2 around. Okay, so the system will still be the same system, except I'm just changing the order of those two equations. I'm essentially flipping them, which doesn't really change anything. So this is 1, 3, minus 1, and then the new second row is 2 minus 1, 1, and then 3 minus 5a. And of course, we have to change what's on the right hand side as well. So this is going to be 4, 5, and b. So with this kind of system, we want to do what's called Gaussian elimination. Okay, so we want to get zeros, if possible, underneath the main diagonal. Okay, so I'm gonna start by converting the 2 and the 3 into zeros, and to do that, we're going to do the following thing. So I'm going to say row 2 minus 2 row 1. That's to get rid of the 2, and then I'm gonna do row 3 minus 3 row 1, and that's to get rid of the 3. Okay, so row 1 stays the same, so that's 1, 3 minus 1, and then let's put the 4 here as well. Now the second row becomes 0, and then we have minus 1 minus 6, which is minus 7, and then this is 1 plus 2 technically, which is 3, and finally we have 5 minus 8, which is minus 3. Okay, now we do the same thing for row 3, and we get 0. We get minus 5 minus 9, which is minus 14, and then we have a plus 3. Okay, and the right hand side term becomes b minus 12, like this. Okay, so the next thing to do would be to get one more 0, which is here. Okay, and we're quite lucky because this term is twice as big as minus 7. So we can now do row 3, and we won't add, but instead we will subtract 2 row 2, like this. So we'll end up with 1, 3 minus 1, and 4, of course, and then we have 0 minus 7 and 3 and minus 3, and then we have 0, we have 0 again. Okay, and then this will become a plus 3 minus 6, which is a minus 3, and then this is b minus 12 plus 6, which is b minus 6. Now I'm gonna rewrite this again. So this is the final form of the matrix, which is 1, 3 minus 1, and then we have 0, -7, and 3, and then we have 0, 0, a minus 3, and b minus 6, and then we have -3 and 4. Okay, and we want to make this system incompatible. Okay, now if a minus 3 is different from 0, right? It would then mean that we have solutions. So if a minus 3 is different from 0, then the system has a unique solution. And essentially, if a minus 3 is anything except 0, then you can find what z is, and then you can go on the second row and you find what y is, and then you find what x is, and you get one unique solution. But that's not what we want. We want the system to have no solutions, because the question is asking us what are a and b such that the three planes don't have any points of intersection. So let's look at the case when a minus 3 is actually equal to 0. So if a minus 3 is 0, the only thing that makes sense is if b minus 6 is also equal to 0, right? And if that's the case, then the system is compatible, but it's indeterminate, so it actually has an infinite number of solutions. Okay, so the only thing remaining is if a is minus 3, if a minus 3 is 0, and if b minus 6 is anything but 0. Okay, and just to give you an example, imagine the final row is 0, 0, 0, right? Because if a minus 3 is 0, then this would be 0. And imagine if b minus 6 would be something like 1, right? Then this doesn't make any sense. It means that 0 times x plus 0 times y plus 0 times z is equal to 1. So, of course, it's nonsensical, right? Because every number here being 0 means that the right hand side has to be 0 by default. And if the right hand side is 0, then this brings us to this second case where we have an infinite number of solutions. So for our system to make no sense, we must have this right hand side equal to anything other than 0, because in that case our system will be incompatible. So the answer for this is we must have a minus 3 as 0. In other words, a should be equal to 3. And b minus 6 should not be equal to 0. In other words, b has to be anything other than 6. So the final solution is, for our system to be incompatible, or geometrically speaking, for the three planes to not have any intersection points, we must have an a equal to 3 and a b which can be anything other than 6. And that's the end of the question.